going to fight with projectors for the next 10 or 20 minutes? It's only getting smaller. Yay! No! Yay! So, you are a researcher in advanced type systems, and you have just developed the type system which will solve the world's programming problems forever, unifying every possible type of language feature into one grand abstraction. And some researchers, upon reading your paper, start asking this awkward question. Do your programs actually run? And of course, you can answer this quite simply. You should, of course they run, see figure 2. But they're quite insistent. They ask, can you make it actually go? And when you've done that, can you make it go fast? So this means you find yourself having to write a compiler. You take as input your wonderful language, and you produce as output some other inferior language in a way that hopefully preserves the semantics. So what you have to decide is, what are you going to target? What are you going to compile to? There are many languages you could compile to. Broadly, we can break them into safe and unsafe languages. In the unsafe languages, if you do something silly, the computer will cite faults and complain. In the safe languages, the compiler will complain. But the trouble is, if you're compiling to a safe language, well, so some of the languages are safe because of types, and some of them are safe because of runtime checks. If you're compiling to a language which is safe because of types, then you have to fit your wonderful type system into the type system of the language you're compiling to, which for some type systems is deeply non-trivial. Like if you have done something interesting with dependent types and you're trying to compile to Haskell, then it's, I mean, not necessarily impossible, but a problem just as big as your original ones. Whereas if you compile to a language that's safe because of runtime type checks, then even though you have written a static type checker which proves that your programs have well-defined behavior, you're still going to incur the cost of checking at runtime that they have well-defined behavior. So for these reasons, it's quite convenient to compile to an unsafe language, because you know that your type checker has no bugs. So you can compile to an unsafe language and know that it's going to run the way you intended and not incur the performance penalty of checking that it's not doing something stupid. Unfortunately, most unsafe languages are very low level. Which means you have to implement, I mean, C doesn't have closures, you have to write closure conversion, which is a pain. C doesn't have garbage collection, you have to write a garbage collector, which is an even bigger pain. And also, the surface syntax of these languages is not terribly pleasant to generate either. You end up just, first of all, there's never any good APIs to generate them, you're just pasting strings together. And secondly, they have, I mean, every language that's intended for humans to write has bizarre scoping rules and reserved words, and you have to be careful to avoid them when you're generating code and so on. So often it's more convenient to generate an intermediate representation. So, like, for instance, instead of generating C, you can generate LLVM, which is like similar semantics, but it has a more regular syntax. Or instead of Java, you could generate JVM bytecode. And instead of Haskell, you could generate core system FC. The intermediate for language for Lisp is, of course, more Lisp. But the trouble is, all of these, they're a bit more pleasant to generate, and some of them have good APIs, but they're all very, very similar to the language that you started with. I mean, system FC, the core language that Haskell uses as intermediate representation, that is a wonderfully designed system which fits Haskell like a glove. But Haskell has infinitely many fingers and higher dimensional thumbs, so it doesn't necessarily fit your language. So slightly unusually, OCaml's intermediate representation is not at all like OCaml. It's a completely unsafe, untyped language. The first thing OCaml does after checking types is throw them all away and convert to basically the untyped lambda calculus. And all of the subsequent stages of the compiler, the optimizations, the one-time behavior, make no reference to the original OCaml types of the program and work purely with this untyped lambda calculus. Which makes it quite an attractive target for other things that are not OCaml. You can compile to this as long as you can express your language in terms of the untyped lambda calculus. So there's a couple of reasons why people don't already use this. Lambda itself is undocumented and has somewhat unclear semantics and doesn't have an API and doesn't have a syntax. So I wrote Malfunction, which is a fairly small project, which gives a syntax to Lambda so that you can actually generate this fairly well-defined, quite straightforward S-expression-based syntax, and then just feed it into the back end of the OCaml compiler and have reasonably efficient code be produced at the other end. So here's the obligatory factorial function. It's actually defined over big integers. Malfunction has a few integer types, mostly fixed width, including big integers using the Zareth OCaml library. As well as having a well-defined S-expression-based syntax, it also has some semantics. As well as the compiler feeding into the back end of OCaml, there's also an interpreter for Malfunction that just runs a program and determines whether or not it actually exhibits well-defined behavior or whether it crashes. And this is quite an important thing if you're compiling to an unsafe language. When you're compiling to C, there are many things in C which are undefined behavior, but the trouble is that there is no way of telling whether a given program has defined behavior or not. There are short 10-line programs that learned scholars have heated arguments about whether they have well-defined behavior. But with this, because the semantics are so much simpler than the semantics of C, you can just run it in the Malfunction interpreter, which is a really stupid 200-line evaluator, and it will tell you whether it is a well-defined behavior or whether it did something that was outside the semantics. So it's very, very easy to compile to. So I wrote a backend for Idris, a dependently typed programming language, based on the PHP backend for Idris.
That's why the variable name. That's why you use the dollar, because you use the ICFP backend code base.
Oh yeah, of course. The entire design of everything should be based on PHP. So about 200 lines of code is enough to write an Idris backend to Malfunction. It's about 199 lines of that, or a great big match over the various things that appear in Idris's intermediate representation. And it runs Idris programs quite quickly. So here is a simple program that's just came with Idris as an example in the previous backend, which searches for Pythagorean triples. And so Idris doesn't have a very comprehensive benchmark suite, so I can't present very detailed numbers. So I just ran this and a few other simple Idris programs that people are using as benchmarks. So take all numbers with massive grains of salt. But I found that when compiled using Malfunction to the OCaml backend, that the performance ranged from 3 times faster than Idris's native C backend to about 13 times faster than Idris's native C backend. So if you're writing a compiler, I would recommend considering compiling to Malfunction because you get to use the pretty high performance OCaml backend in its mature GC, and you can get very reasonable performance with very, very little effort. Thank you.
Okay. So this is wonderful. So arguably, you created a new list, right? But there are all kinds of lists come with the compiler switch that lets you turn off the checks, right? And there used to be even an OCaml implementation based on Manuel Serrano's scheme system. It was back that was quite competitive. Do you have any idea if you tried, like just emitting lists and seeing how competitive that is with your stuff?
Not really.
Somebody should do that.
I have also an answer to this question. So, for example, SBCL would be usable, but it doesn't have a built-in representation for algebraic data types. And the value representation in OCaml is fairly good. So if your language uses algebraic data types a lot, I think Malfunction has an edge on like spitting out Lisp code and feeding it to SBCL. I think. I have not tried.
So can you interact with OCaml
Yeah.
libraries and modules?
Yep. So you can link against OCaml code.
Okay, so it creates CMIs and stuff?
Yep. I have not, I mean, the interpreter doesn't do that. They reference semantics, but when you actually run the code, it'll link against OCaml code.
Is there also a way to reflect on the CMIs, like when you need to import stuff?
At runtime, or?
No, I compile so that I can read them. Is there an aspect of reading CMIs that I want to import in my model?
You can reference them by name, but there's no API for like iterating over them.
Your compiler library has that. You won't generate CMIs. You generate CMOs and CMX. You don't generate the type of OCaml. You don't link OCaml to that.
Oh,
That to OCaml.
no, that's actually untrue. I do generate CMIs, and you can link OCaml to that. The CMIs are not very interesting. They don't give detailed type information. They just say it exists.
Just give me a question. I'm very curious. How comes the name?
This was a project which started from an entertaining pun and worked backwards to an implementation. It also refers to the behavior that you get when you start typing random things into it.
So, the Idris implementation is that Idris is written in Haskell, isn't it?
Yeah.
So if you generate the S expressions and then run it through Malfunction.
Yep.
What seems slightly peculiar about that is I think Idris has a whole series of different intermediate representations.
Yep.
And isn't one of them essentially untagged grammar characters as well?
Oh yeah, yeah.
So is that why it's so peculiar?
Yeah. I mean, it's got slightly different treatment of algebraic data types, so the representation isn't completely trivial, but it's very close to trivial.
Also, Edwin, I think, did a whole load of work on doing the same kind of thing that you're doing, in terms of he wanted to be able to have, to use, he had a system that allowed you to target lots of different languages in the same get the same performance. But I don't, do you know how your work relates to his?
Oh, sorry, yeah, it's of course thanks to Edwin's work that it was only 200 lines to write a backend for Aegis. I mean, he has, like, it's quite pleasant to write new backends for Aegis. That doesn't sound like what you were asking there.
No, I think he had a system to use as a backend for arbitrary programming languages. I think it's the same as Idris. Sorry, I should talk.
Yeah, okay. Thank you.